Hello, I'm David. I'm the coordinator of the Maths Learning Centre here at the Uni of Adelaide. It's semester 2, 2024, and this is a revision seminar for real analysis. And we're just going to have to decide what we want to talk about first. And so I thought maybe we could do a bit of a brainstorm about what the course is kind of about. I'm just going to pause recording and I'll be back in just a second. All right. So real analysis is about all the theory behind how the calculus of real numbers works, right? Let's see if we can remember what's in the course. Somewhere near the beginning, there was some stuff about what the real numbers are. It came about that what they are is a field, and there were some field axioms that they had to satisfy. And it also had that actually they're ordered as well, and there were some axioms for how the ordering on real numbers works, the less than or equal to ordering works. Cool. And then, well, there was definitely stuff about suprema and infima along the way. Oh, and then there's also something about them being uncountable, right? And so there was bits about countability and uncountability near the beginning too, yeah. Okay. And the definition of complete was what? The existence of least upper bound. And once you're at that point, you had to talk about least upper bounds, i.e. suprema. Sups and infs. Yep. Density. Okay. Cool. All right. Yeah. That's actually a lot more than I thought. Interesting. And then there's definitely along the way things about limits of both sequences and functions. This is not in the order that the course is, but and there's definitely along the way somewhere derivatives are in there somewhere. And I'm presuming the intermediate value theorem is sort of nearby to derivatives, but not necessarily right there. So there'd be like when you're having functions and when you're doing limits and functions, there's continuity. And that's where the intermediate value theorem is. And then, and the mean value theorem is the one that goes with this. Were there any other derivative theorems? It's all right if there aren't. That's the main one. There you go. So the definition, the derivatives would have had a definition of some sort via limits, though, right? It's still the traditional definition with the h goes to zero, like x goes to a of, yep. And then there would also be, yeah, f of x minus f of a over x minus a, that thing. Yep. As a limit. Sweet, cool, cool, cool. And then, and a lot of the things that we know to be true about derivatives like concavity and increasingness and that sort of thing come from the mean value theorem ultimately, and then when they keep getting it to prove those. And then there's also integrals, yeah? And they have like partitions and upper and lower things, and they've got theorems too, right? There's at least one theorem that I used to know a theorem called the average value theorem, but hmm. Oh, the fundamental theorem of calculus. Right, yeah, that's the theorem. Oh, and at the very end they did talk about logs. Um, and I think what I'm missing is series, like infinite sums. Ah, yeah. I think that's pretty much everything. That feels everything. Ness. We've put a lot more detail here than in all the others, even though this was the smallest bit of the course. But yeah, okay. Um, and somewhere along the lines with the open and closed sets, there's a definition of compact as well. And so there would have to be a concept of boundedness in there too. Okay, radio and sequences would have had Cauchy-ness in there somewhere, yeah? Yeah. Radio. Okay. Okay. Um, So that seems to be a fairly comprehensive list of the topics. But you know, it's very good for you if you're ever doing a course like this, and those of you watching the video, um, it's good for you to try to remember what the topics in the course are, so that you can feel better about them. Now that we have got a list of topics in the course, anything stand out that you want to talk about? That's all. That's all good. That's a nice place to be if you're feeling like that. Um, yeah. Mm-hmm. Yeah. Sure. You could email it to me, like the same email where you found out about the revision seminar. I will just pause the recording again while we sort that out. All right, I've been sent a list of questions that the lecturer made, um, and we're going to have a look at them. And there's 1 to 6, and they've all got an A and B, and I'm going to randomly pick one and see what we get. So I'm just going to go to my random number generator. Oh, it would have been quicker to get R up. Okay, it's my random number generator says question 4, part A. All right, here we go. Did I actually share this? Yes, I did. Okay. Is there an integrable function g, which sends 1, 3 to r, such that h of x, which is equal to the integral from 1 to x of g for all x in 1, 3, where h is the function from question 3b. Oh, well, looks like we're doing question 3b first. Okay. Question 3b. Consider the function h, which sends the interval from 1 to 3 to r, which is h of x is 4 minus x if x is between 1 and 2, but not including 2, and 1 if x is equal to 2, and minus x minus 2 squared if x is between 2 and 3, also not including 2, but including 3. Sketch h, is it integrable? Well, even without sketching it, my guess is that it is indeed integrable. The reason I think that is that this is a continuous function here, and this is a continuous function here, and I'm almost certain that functions are integrable as long as they only have a small number of discontinuities. And the only place it can possibly have a discontinuity is at the place where x is equal to 2. Yeah? Seems reasonable to me, but I shall still sketch it anyway. There's 1, 2, 3. And 4 minus x is a straight line with slope minus 1. And when x is 1, it would be 4 minus 1, which is 3. And when x is 2, it would be 4 minus 2, which is 2. So that part there from 1 to 2 would look like this because it's a straight line. And then the answer when x is 2 is 1. So that's definitely a discontinuity there. And minus x minus 2 squared. Well, x squared would look like, minus x squared would look like that. And x minus 2 squared would shift that to be at position 2. And so it's going to go down like this to 3 minus 2 squared, which is 1. So kind of like that. Let's check if I put 3 into this formula. 3 minus 2 is 1, and 1 squared is 1, and minus 1. Okay. There is my sketch. Things I notice about this function is a discontinuity when x is equal to 2. It's also monotone decreasing because no matter which two x's you pick, the later x has a lower value of y. So that's cool. So I think that this function, actually that's probably, it's supposed to level off, right? That's probably more accurate, but anyway, doesn't matter. Okay. So functions are integrable if, what's the definition of integrability? If the integral exists, then it is the infimum of all the upper sums and the supremum of all the lower sums, right? This is where I need to look it up. I'm pretty sure that's the definition in real analysis. Let's look it up. $63. Yeah. And the lower integral is the supremum of all the lower sums. Yeah. Yep. This is the one from his book. It's Finner, right? This here. Yeah, this is Finner's book. It's integrable if those two things are the same. And there's a lemma. Not a lemma. A monotone function is integrable. This function is monotone. And so that's useful to know because it is monotone. Oh, okay. So no matter what partition you happen to draw of, whatever, no matter what partition you happen to draw, the supremum on every interval would be the value at the left-hand end. Like on a particular interval, this interval here, the supremum of the function on that interval is the value at the left-hand end, and the infimum is the value at the right-hand end. And so the supremum on every interval is the infimum on the next, the infimum on every interval is the supremum on the next interval, and so your the difference between your upper sum and your lower sum is just the difference between this height and this height, like times the little width, right? Because you multiply them all by the width that goes with them, yeah? Oh, crap. So just better do that. The definition of this lower sum, yeah, okay. So each interval has a width, delta x, I, and the lower sum, like the little mi, is the infimum of the values of x, where x is in interval number I, right? Something like that. That's probably not how he called it. Like I'm just thinking of it made of a sequence of intervals. Yeah. And then the lower sum that goes with that partition. So the partition is, I1 union up to IN, something like that. And the lower sum that goes with the partition of the function with the partition is the sum of mi delta xi, something like that. Okay. And that's the width, right, of xi, of interval I is delta xi. That's how I think about it, where delta xi is the width of interval number I. But I think your lecturer has a list of x's which are x0 up to xn. x0, x1, x2, x3, all the way up to xn. And he writes all of his things in terms of the x's, whereas for me, like this is delta x1, and this is interval number 1. So that's how I think about it. It's the same thing. Okay, cool. And so if you do have a decreasing function, the infimum on interval number I is the same as the supremum on interval number I plus 1. And so when you subtract the two of them, all the ones in the middle will cancel out. Yeah, okay. So that's the proof here. Yeah. But we have to do a bit of fiddling with less than or equal to's because our intervals aren't all the same width. So in Maths 1A, they all cancelled out because the widths were all the same as well. But in this one, we can just make sure that the intervals are small enough to make everything less than the number you want. So yeah, basically you just need to make that the intervals at the end are narrow enough to figure it all out. Okay, that's not too bad. I'm all good with that. Okay, so the vibe of this question is it integrable? Is to us to know the theorem that it's integral because it's monotone, and that is theorem 7.6. A partition is a list of intervals that makes up the big interval that you're integrating across. No. Yep, partition. The official meaning of partition in mathematics in all places where they use mathematics is it has to cover everything. So, no gaps. Good question. So that's one of the reasons why your lecturer doesn't talk about them as intervals and talks them about a list of x's. Because you have a list of x's that starts at the beginning of the big interval and ends at the end of the big interval, and then has all these x's in the middle, and all the intervals are the ones spaces between the x's. And so there's no gaps because that's just how you define it. Yeah. Yeah. So it has to cover everything, and they have to be disjoint. Well, I mean, they're allowed to share their end. The beginning of one is the end of the previous one. So we're just going to add that to the thing, a partition. Disjoint, or just sharing endpoints. And it has to cover everything. Did the lecturer talk about just a second, equivalence relations in this course? Was that in algebra? Okay, all right. So equivalence relations produce partitions as well, in a similar way. But like, yeah, you have to cover everything. Yeah. Yeah. So that's fine. Okay. So basically question 3B was pretty much just requiring us to know theorem 7.6. Okay. Right. Interesting. We've learned a little bit about the mind of the lecturer here. Okay. All right. Now I was actually aiming to do question 4A. Is there an integrable function g that is an integrable function g which sends 1, 3 to R such that h of x is the integral from 1 to x of g? Okay. Well, that's asking if h is the derivative of something. Because the fundamental theorem of calculus, part 1, I think, does your lecturer do the fundamental theorem of calculus in 2 parts? The fundamental theorem of calculus in part one. Part one says that if you have an integrable function and you create... No, just a second. Wait, I think I said it wrong before. If you have an integrable function g and you create a new function, which is the running total integral. So in my head, this is called a running integral. I don't think that's what your lecturer calls it. I don't think he has a name for it. But if you have a running integral function, then the derivative of the running integral function has to be g. Like the derivative of an integral is the original function. That's fundamental theorem part one. And fundamental theorem part two is that the integral of a function is an antiderivative. And so if it was true, then h dashed x would have to be equal to g of x. Yeah. By fundamental theorem of calculus part one. Yeah. Because the fundamental theorem of calculus part one says that the running integral of an integrable function is a differentiable function. And so we would have to know, therefore, h dash of x would have to be differentiable, which it's not because it's not continuous. So just continue on. So my running integral function could only work up to the point 2, but not beyond that. But h of x is not continuous on 1, 3, so it's not differentiable on 1, 3. So no, g does not exist. It can't exist. Because this is not differentiable. This function cannot describe the running integral of another function, because running integrals do not have discontinuities. And just to be absolutely certain about this, if this was the running integral of another function, then it would be saying that we start at 1 with... Well, the other thing is that h can't be the running integral of another function because where the integral starts at 1, because it would be 0 at this point too. Like the integral from 1 to 1 of g would be 0, right? And so h of 1 would have to be 0, and it's not. And so this cannot be a running integral function because it's not 0 at the appropriate point. Yeah. But if I change the question, like, even if this wasn't a 1, if it was just an a, right here, for a in 1, 3, then this answer would cover it for any a. So, yeah. Because technically, if you start at position a, then you can integrate something backwards and get a negative number. But yeah, but also to be fair, h is never 0, and so it can't be a running integral of anything because the running integral function is always 0 somewhere. Oh, that's so cool. All right, so we have 2 reasons. So that was reason 1, or reason 2 is that if h of x was the integral from 1 to x of g, then h of 1 would be the integral from 1 to 1 of g, which is 0. But h of 1 is in fact 3, not 0. That's the other reason. That's so cool. And if I had this exam question and I noticed both of those things, I would write them both down to prove that I knew them both, just in case. Yeah. Fascinating. So just riffing off of that, just want to be absolutely sure, just imagining if I had just some function like that, let's call this g, and I did the integral, and this is going to be the running integral from let's call that 1, from 1 to x of g. Then at 1, the answer would be 0. And then the integral would increase until we got to this point. But it would still be increasing at this point because the area is still above the x-axis. So it would go like this, and then it would go like this, because it increases slower and slower and slower until at this point, it stops increasing, and the area, we start adding negative areas, and so it's going to start decreasing now. And then, oh crap, not. I'm just going to extend this outwards a little so that I can draw my graph a bit better. All right, that's better. And then it starts decreasing. And then it will, at this point here, continue to decrease because it's more and more negative, but it will decrease like at a constant rate. Yeah. And so it has to start at 0 at whatever point you start your integral. Yeah. And it has to be continuous because of the way that you keep adding little slices of area, you can't make jumps. The only way to make a jump would be to somehow suddenly add a lot of area at this spot, which you just can't do. Though people who do differential equations created a function that can do that, which is called the delta function. Yeah. If this graph jumps though, like that maybe. That's my g, and this is the integral from 1 to x of g. So we start at 0, integral starts going up until this point, and then it starts increasing at a constant rate at this point. And the thing is, if I move a teensy tiny bit forward there, I add a teensy tiny bit of area here, and so this doesn't move very far. And so if I just zoom in on this and just add a teeny tiny bit move forward there, then I add a teeny tiny bit of area, and it just starts going up, right? It's still going up from that point. A jump doesn't stop it from doing that. It just changes what the slope at this spot is. Like in the top graph, where it's not like close, right? Yeah. Sorry, where? Oh, here is. Yep. Yep. And then I get that that corresponds to like a straight line. Mm-hmm. But then the amount of area that you're adding is less after that jump. Less than what? Oh, what that is? Yes, sorry, the slope should be less. So you're saying that it should start out going like that. The slope is less. Yeah, but this is the running total area. And so the slope is less, but it's still adding extra area. It's just doing it slow. You're right. It's adding extra area slower than it was here, and slower and slower and slower until we get to there. And then it suddenly starts adding a whole lot of negative area all at once. Yeah. So even if this function has a discontinuity, this function doesn't. And when you differentiate this, I believe this one's actually smooth at this point. Like they in fact line up probably, yes. This will in fact be curved, but happen to line up to this slope here. Those slopes will match at that point. But you're right, these two slopes here, when we zoom into them, it'll be going like that, right? And so technically the derivative of this function isn't continuous. That's okay, because it shouldn't be. Yeah. Okay. Earlier. So if it was true, then H dash would be G by the fundamental theorem of calculus part 1, but H isn't continuous, so it's not differentiable. I mean, it's differentiable at most places on 1,3. It's just not differentiable at one place. So. Yeah. Right. Cool. So the fundamental theorem of calculus only applies to continuous functions, doesn't it? So technically this doesn't apply to G because FH because it's not continuous. Fundamental theorem of calculus says that the running integral of a continuous function is differentiable. Now, I think we're going to have to scrap this one. I mean, it's still true, but I think that technically you can't use the fundamental theorem of calculus for a function that's not continuous because of exactly what I was saying here of the if when you differentiate this, you end up with open circles at both of these places and no answer at all on that line. But even if this had an answer on this line, it still wouldn't make any difference to this graph. And so when you integrate this, you get this. And when you differentiate this, there's nothing on this line. And so, yeah. No, I think that, I don't know. Anyway. No. Oh, no, they want G to be integrable. That's okay. It's fine. Yep, no, this is fine. I'm getting confused about which function is being integrated and which one's being differentiated. It's H that's the integral, isn't it? Okay, it's still okay. I'm all good. Oh, is it? I thought the second, oh, damn it. I'll have to look it up. Oh, is it? Oh, that's the opposite way around to how it is in Maths 1B. Cool, sorry. Page 67, apparently. Oh, okay, it's part 2. All right, thank you. Those parts are listed the opposite way around in Maths 1B. So helpful. Oh. Okay, fine. Okay, Cool. I like that there's two reasons. This is my preferred reason. But if it was 0 at that point on the graph, if they had given us one that was 0 here and went up like that first, then it could have been except for the discontinuity. Okay. Right, okay. Well, actually, we ended up talking about a lot more than we expected with that question, which is for you, this and all of us, this is an important thing about when you do problems in especially a pure maths course. You really want to try and suck as much juice out of them as you can by asking lots of what ifs and saying, well, what does this tell me about the theorems and about the facts that are in this course? Now, have you been inspired to ask any other questions? Or do you want me to pick another random one? Free part A, okay. That's what it says to do. Okay. All right, 3 part A says let I be an interval and f sends I to R is differentiable. And there are distinct A and B in the interval, with f of A being A and f of B being B. Okay. Prove that there is a C in the interval with f dash of C is in fact equal to 1. Doesn't sound good. Okay, that's what it says. It's supposed to be an arrow. All right, well, my instincts, there are 3 theorems that I'm familiar with in the calculus theorems that I'm familiar with that tell you the existence of a number, like a point that does stuff. So there's the intermediate value theorem that says that there exists a point that has a particular function value. And there's Rolle's theorem, which says that there's a particular point where the derivative is 0, and the mean value theorem, which says there's a particular point where the derivative is calculation involving the endpoints. So it seems to me that the mean value theorem would be the go, because I want a point where the derivative comes out to a specific answer that isn't 0. That's my thinking. Mean value theorem says there exists a C where f dash of C is a number. That's what I'm imagining. And so mean value theorem seems to be the thing I should use. And so I'm going to just draw a picture of said interval. Here's A, here's B. They're both in I, but I don't really care where I is, so I reckon. And f of A is A, and f of B is B. So I think we should probably start by saying, well, we're just going to assume that B is more than A, because I don't think it matters, because otherwise we can just switch which one's called A and which one's called B. And that slope is 1, right? Because that's the line y equals x. And so the mean value theorem says that no matter what the function actually looks like, there must be a point that has that slope. And that's the C we're looking at. So this doesn't look like it's going to be too hard to do, I reckon. I think we're right there. Yeah, but f of B is B and f of A is A. So that Yeah, that's great. So according to the mean, so I think we should say since A and is not equal to B, we can assume A is less than B. Might as well start with that. And then so we know that there is a C in the interval from A to B. Actually, it's an open interval, isn't it? In the open interval from A to B, such that f dashed of C is f of B minus f of A over B minus A. So that is by the mean value theorem. And that is B minus A over B minus A, which is 1. Cool. How unsatisfying. Okay. Have you ever done the proof that if the derivative of a function is positive on an interval, then the function is increasing on the interval? Oh, was it? Yeah. Because that's a mean value theorem proof. Okay. So do you want me to do that one or not? You've done that one before? Well, let me make up another one. Yeah. I mean, the one like you can, yeah, that's one of the classic proofs that I know that proves things using the mean value theorem. So we don't have to do that. It was just worth a try. I'm going to say suppose F, which sends A, B. Wait just a second. I'm going to try one and see if I can make it work. Okay. Suppose F sends R to R. Yep. And F dashed of the point A is differentiable. Right. And F dashed of A is strictly positive. Yep. Then there is an interval I containing A such that F is strictly increasing on I. That is my proof. That's my thing that I think is true. We'll know if it's true soon. So that is slightly different to the thing you had in your assignment, right? So this is basically saying that a function is increasing at a point where the derivative is positive. But it's saying that there is an interval around that where it is increasing. So the first thing I do when I do any of these problems is I imagine my function, and here's A, and here's a spot, and that's the f dashed of A, that slope. So what they're saying is that no matter what the function is doing at this point, as long as it's differentiable here, then there will be a spot nearby, like an interval around this, where it's increasing. Okay. Right. I've made it hard for myself. I do know what the derivative is, right? It's a limit of something. So I know that f dashed of a is the limit as x goes to a of f of x minus f of a over x minus a. Yep. And since that limit exists, that means that for every delta, no, for every epsilon greater than 0, just saying, I think I've got it. But the definition of this limit being that is saying that for every epsilon greater than 0, there is a delta greater than 0 such that if the distance between x and a is less than delta, then the distance between f of x minus f of a over x minus a and f dashed of a is less than epsilon. Because this is the thing that we would normally be calling f of x. And this is the thing we'd normally be calling L for limit. So I definitely know that, right? So f dashed of a is a positive number. So if I'm close enough to a positive number, then if this is close enough to being a positive number, then this will have to be positive as well. Because if you pick any positive number, then if you get close enough to it, then you're positive as well. Because the negative numbers are far away from a specific positive number. That's what I'm thinking. If I made epsilon equal to f dashed of a, like if I just have a random positive number like 0.1, and I pick numbers very close to 0.1, they'll be 0.11 and 0.09, which are also positive. So I can guarantee that there is a zone around, but I can guarantee that this is definitely a positive number. And so I'm going to say choose epsilon to be equal to like f dashed a on 2, which is positive. Yep. And then there is a delta such that for x minus a being less than delta, f of x minus f of a over x minus a minus f dashed of a is less than f dashed of a on 2. Doesn't even need to be f dashed of a on 2. Oh, kind of just do f dashed of a. And that means that this number is between that and minus that. Like that. And if I add f dashed of a to everything, I get this. Like that. And therefore, in particular, this is definitely positive. Hey, okay. So I f of x minus f of a over x minus a is greater than 0. Yep. And so therefore f of x minus f of a is greater than 0. And therefore f of x is greater than f of a. Hmm. Oh, not necessarily. It depends whether x is more or less than a. Because if x minus a is negative, that would become a less than 0. I might come back to here and just leave it at that for the moment. So, oh crap, I don't think this is going to help. Anyway, I do know for sure that this slope between the point A and X is definitely positive everywhere in this little interval from X minus delta, A minus delta to A plus delta. So far we have, for X in the interval from from A minus delta to A plus delta, f of X minus f of A over x minus a is greater than 0. We definitely know that to be true, but that doesn't mean it's increasing on this interval necessarily, because all we're doing is comparing to the center of the interval rather than from any point to any other point. Okay, so no, that's okay. We're just comparing to A, right? So what about another one? Let x and y be in this interval. Then what we want to show is that f of with y greater than x. And what we want to show is that f of y is also more than f of x, because we want to show it's increasing. So f of y minus f of x, we would like to show that to be a positive number, because then that would mean f of y is more than f of x. Okay. Oh, I don't want to do cases. I was sort of hoping that I wouldn't have to do like, what if they're both less than A, and what if they're both more than A, and what if what if one's on either side? I didn't want to do that. Damn it. I thought I had it. It might not be true, but I'm almost certain it's true. I was trying to show it was increasing on that whole interval, but, oh wait, I haven't used the mean value theorem yet. No, but it does have derivatives everywhere. It says it was differentiable everywhere. Ah, aha. I have it. It's the cutest little magic trick. You ready? It's so good. It's so good. Okay. Is it? Oh no. I thought I had it. Damn it. Bear with me. I thought I had that I might be able to borrow what I've done here. Like what we know is, okay, no, I am going to do what I did before. Okay, so if x is before, I really wouldn't, no, it doesn't matter. I was going to say, so if x is less than a, yeah, then x minus a is negative. And so this becomes this when I multiply both parts by x minus a. And so therefore f of x is less than f of a. And if x is more than a, then x minus a is positive. So f of x minus f of a is greater than 0, becomes f of x minus f of a is positive, and therefore f of x is greater than f of a. Right. So definitely, if you are at a point where the derivative is positive, then there is a zone around it where everything on the right hand is above a, f of a, and everything on the left hand is below f of a. That is definitely true. So what we have here is that here is a, and here is a minus delta, and here's a plus delta, and we have an f of a here, and here this is f of x is less than f of a, and here f of x is more than f of a. That's what we know so far. As long as the derivative is positive everywhere in there. Okay. Oh, I really made it hard for myself. You should never make up questions on the spot. But that's okay. It's still good for me. We've thought about some cool stuff along the way. Well, I'd be happy. This isn't the actual answer I had, but it's still something that's worth noting. It feels increasing, right? Because on one side, the function value is higher, and on the other side, the function value is lower. But I'm not sure if it's actually increasing in everywhere, because to be properly increasing in this interval, I need to pick anything in here and anything else in here and be able to do it. But I do know definitely that on this, anything, any value here and any value has a higher f value than any value here. I do know that. Well, we're still on either side of A though, right? My question is, I don't know whether it's increasing in this zone. Do you know what? I don't think it's true. When you say something's differentiable, does that mean that the derivative is continuous? No, it just means the derivative exists at every point, yeah? There's a differentiable at a point. Hmm. How do you arrange for the derivative to be? Give me a second. Critical points. Well, here we go, just a second. Here we go. Although derivatives need not be continuous, they do satisfy the intermediate value theorem. That's theorem 6.12. F dash of A is less than S is less than F dash of B. Find G of AB goes to R. G of X is S of X minus F of X. Then G is differentiable. Wait, I think I have it now that I've thought about this and let my mind think about this in the background for a bit and said some words. If I pick a point in this zone, then so I know that F of A plus delta is more than F of A. Well, maybe A plus delta minus a bit. Okay. I was just thinking this point here, its derivative, there is a, no, thought I had it with the mean value theorem. I mean, if I knew that all the derivatives at all these points was positive, I'd be okay. But I'm stuck. Like I have a feeling that it's not true unless F is continuously differentiable. So I may give up on this for the moment. Might be a question to say, I made up this question, Finna. What do you think of it? And are there functions that make it not true? Because there's all those crazy functions like the Dirichlet function and whatever that turn out, not the Dirichlet function itself, but turn out to be differentiable, even though it's like the derivative is like discontinuous at every point or something ridiculous. So that might be what's causing my problem. So I probably need it to be continuously differentiable. Because if it's continuously differentiable, then the derivative is continuous, which means that if the derivative is positive at one point, it must be positive at all the points nearby, because that's how continuous functions work. I've really thought I had it. That's okay. Well, worth a try. Worth a try. I have at least proved something, right? That if the derivative is positive at some point, then there is a spot where all the points to the right have a higher function value and all the points to the left have a lower function value. And so it's definitely increasing if you think of only points from here to here. The question is, what about the points from here to here? Yeah. There are definitely infinitely many points in, well, there are definitely many points in here whose derivative is positive. Because if I pick any point C, so if C is between A and A plus delta, then there exists a D between A and C with f dashed of D being equal to f of C minus f of A over C minus A. And both of these numbers are positive because we already proved that. And so therefore that's positive. So there's definitely another point somewhere in the middle where the derivative is positive there. Huh. Right. But if you had two of them, like a C1 and a C2, you couldn't necessarily guarantee that both of those D's were like that C2's derivative would, yeah. All right, that's okay. I'm all good. Because you could recast to have D as your, see now the derivative of D is positive, and so you could do everything in terms of D instead. But it's fine. I am now going to be content with if B is between A minus D and A, and C is between A and A plus delta. Sorry, that's a delta. Then f of C is more than f of B. That is definitely what I know this to be true because f of A is between them. Okay, that is it. So it is, maybe this is not true. Not sure if original proposition is true. Okay, well, there you go. And if I was in an exam and I was at this stage, I would just leave it at this and say, well, I mean, if my lecturer had asked me to prove it, I would assume that it's true. But I would get to this point and go, well, this is the best I can do. And I would say, I know this isn't where I was supposed to go, but it's something. Yeah. Okay. Well, if anything, there's some life lessons there about what to do if you don't know what to do. One of the problems with that some people do face in the course like real analysis is if they can't see how to prove it, they don't do anything. Whereas what I've got is at least something. I've proven that I understand what the definition of the derivative is, at least. Yeah. Okay. That's fine. I have one more. I just want to adjust the question. What if f of x is continuously differentiable? Can I do the proof then? I'm going to wonder about that. So if f of x is continuously differentiable, then f dashed x is continuous. Yeah. And therefore, how does the limit continuous functions. So the f of x is dashed x is continuous, and so that means that the limit as x approaches a of f dashed of x is in fact equal to f of a. Yep. Because that's what continuity f dashed of a, sorry. F dashed is continuous, so the limit as you go to any particular spot is the same as the function value. Yeah. And therefore, so for epsilon equal to f dashed of a, there exists a delta greater than 0 such that when x minus delta is x minus A is less than delta, the distance between f dashed x and f of a dashed of a is less than epsilon, which is f dashed of a. And so minus f dashed of a and so 0. Same reasoning I did before, but with f dashed of a directly. Like that. And so therefore f dashed of x is definitely positive for every number in that zone. I can be sure about that. Yep, and so now I'm good. I can do it with the intermediate I can now use your theorem from the assignment that said that if you have a function so that at every point the derivative is positive, then it's an increasing function. So we can do the same thing that you already did in the other assignment. So now let B and C be in the interval A minus delta, A plus delta. Then there exists a D between B and C, with B less than C. There exists a D between B and C so that f dashed of C is equal to f of B minus f of, so f of C minus f of B over C minus B by the mean value theorem. Which is a positive number. F dashed of, that's not C, that's a D. F dashed of D is positive because they're all positive for everything in this spot. And so therefore f of C minus f of B over C minus B is greater than 0. And therefore f of C is greater than f of B with 2 steps of working. Okay. And so f is increasing on the interval A minus delta, A plus delta, which is an interval that contains A. Okay, so we can do it if it's continuously differentiable and it's much, much easier. Okay. Well, I feel better now. Cool. Well, do you want to stop or do you want to try one more of these problems? We'll pop them back on. Got a series. We've got use the definition of derivative to prove the derivative is whatever it is. Oh wow. They look hard. Yeah. All right. Question 2B. Is there a continuous function f which sends R to R such that f of the entire of R is R without the number 0? Justify your answer. Like, don't say justify it. Of course you have to justify your answer. You're not going to give me a mark if I just say no or yes. Like, yeah, sorry. So if there really is one, then I have to tell the person reading it what it is. And if there isn't one, I have to tell them why. Well, I know that like a rational function, like 1 over x, and I know that's not a continuous function, but 1 over x produces as its answers everything except 0. And like 1 over x minus 2 produces everything except 0 as well. But that doesn't help because that's not a continuous function. No, there isn't. Because of the intermediate value theorem. Because my function is capable of producing positive numbers and it's capable of producing negative numbers, and so therefore it must be capable of producing every number in between, including 0. Ah, yes. A continuous function satisfies the intermediate value theorem. Yeah. And that's how we know this to be true. That's a theorem. I don't know which number it is, but it doesn't matter. And so suppose A is in R such that f of A is negative and B is in R such that f of B is positive, which must be possible if the range is f without 0. Yep. Then since 0 is between f of A and f of B, there is a C such that f of C is 0, like between A and B. Because of the intermediate value theorem, it says that every number between f of A and f of B has a C that produces it. So if both positive and negative, so for a continuous function, if both positive and negative numbers are in the range, then so is 0. Yeah. Continuous and has both positive and negative numbers in the range, 0 must also be in the range. So no, range can't be R without 0. Yeah. Oh, it seems so hard. But as I said just the other day, things that are impossible are easier because you cannot find an example because there isn't one. Finding examples is always hard. Right. Don't know what made me think of the intermediate value theorem, but I can say what was going on in my head when I was thinking about this. What was happening in my head is I was trying to picture what this function would look like. And I was thinking about being continuous. I was thinking about continuity, and I was thinking about how continuity means that if you're at a point anywhere, then all the points nearby are also near to it. And I thought, okay, well, that would mean that if I was at a point that was positive, then all the points nearby would also be positive, and that didn't help me at all. But then I was thinking, well, that would be true for both the positive numbers and the negative numbers. So if the range was R without 0 and it was continuous, like if the range didn't include 0 and it was continuous, then if you were positive, you could only be positive. Like that's what I was thinking. Like if it doesn't include 0, So it can't, that means it can't cross this line. And so I was thinking that it would have to not be able to cross the x-axis because it can't be 0. And if it's continuous, you would have to draw a continuous line that doesn't cross the x-axis, which means it would have to all be positive. And then that made me think, oh yeah, if it's on both sides, it has to cross the x-axis. So yeah, that was my thought process, but not in those words, but that was what was going on in my head. Okay. Well, I think we're just going to stop. Thank you so much. And I'm sure, I'm hoping those watching this online, you can say a big thank you to Charlotte. Sorry, Georgia. Anyway, because she stuck around so that you could have a revision seminar. So thank you very much.